Talk about Schiffer variations and
All right, I'd like to thank the organizers for the invitation to speak. And I've been here for 2 weeks, and it's been great. I've been able to get a lot of work done, and the arrangements have been very fine and very smooth. It's been a great break for me. All right, so I'm going to speak, in fact, about Abelian differentials. And the last 10 years have been a period of very high activity of studying families of Abelian differentials, in particular studying the flow on the space of Abelian differentials. And this is a lift of the geodesic flow for the Teichmuller metric. And so I'm going to spend the first part of the talk giving you kind of a quick run through of some of the very fine results in the last decade, although actually only a few of them. And in particular, to give you some context for this, the Fields Medal citation for Mariam Mirzakhani contains two main contributions. So there's the first, which is my favorite, which is all her work about the Weil-Petersen metric. But the really more substantial and more notable achievements, in fact, are for her work, particularly joint with Alex Eskin and Amir Mohammadadi, on the geodesic flow on the space of flat structures, or if you like, on the space of translation surfaces. So I want to give a kind of quick overview of, or if you like, an entree to what these results are about and what that's all about. All right, and then I realized also there's the irony. So for Rafe, this is a matter that he's having to travel to England to hear, I guess, a summary, which he could just go down the hallway if he had stayed at home. But I guess this was easier. All right. So Teichmuller, recall, started his study of Riemann surfaces, or mapping between Riemann surfaces. So he considered the question, given two Riemann surfaces, he was looking for a minimization question of a very efficient map. And the quantity he looked at, so I'm going to give it, in a sense, more conceptually, he considered the dilatation of a map. And here, dilatation means how much z bar there is in a map. And then he looked at the quantity where you take the soup over the surface of the dilatation, and then you take the infimum over homotopic maps. So this is a mapping question, and I guess it's really one of the earliest ones. So the Teichmuller found that so these are compact Riemann surfaces, found that this has a unique minimum, and the unique minimum is a map that we're going to see in the right coordinates. It's an affine stretch. Now it has singularities, but this is the basic description of it. So I want to remind you a little about the map, because there's this shows us something else. And so that he found that, so I'm describing Teichmuller's theorem, he found that there's a unique minimum, and that corresponding to the minimum, there's an associated holomorphic quadratic differential. And so, in fact, the following is the case. That if you look at the z bar derivative of the map over the z derivative, this is a tensor, and he found that it's equal to a constant that I'll describe times absolute value of phi bar over phi. So this is a constant between 0 and 1. And phi is a holomorphic quadratic differential. Now, what Teichmüller was thinking of and very well aware of. So he's very well aware of what the extremal maps are, mapping between two rectangles in the plane. And this is, if you like, the invariant form of that on a Riemann surface, because you don't have a global coordinate. Well, there's an implied coordinate here. So the implied coordinate that comes with the holomorphic quadratic differential is the antiderivative of the square root. And the beautiful, or his map, or actually, when there's an obvious solution of this equation in this form, and that's the Teichmüller map in local, the extremal map in local coordinates. What is that solution of this PDE? So in fact, it's easier if you don't think about it as a PDE and just try to guess the answer. This map in this coordinate is the solution of this equation. So in this local coordinate, it's an affine stretch. Now, we know what this does then geometrically. So you're adding on k amount of z bar. Well, this gives you a stretch in the x-axis, a uniform stretch, and a uniform shrink in the y-axis. Which x and y? The x and y of this variable. Or to go back to here, these are the so-called horizontal and vertical foliations that come with the holomorphic quadratic differential. In particular, the horizontal is where it's positive, and the vertical is where it's negative. Remember, this is a square root. All right. Great. So further part of Teichmüller's theorem is that these maps parameterize Teichmüller space. And that is the following. If we consider k, which is in the interval 0 to 1, and then we consider the space of holomorphic quadratic differentials, and I'm using R as the base surface. We consider this, but modulo R plus, acting by multiplication. So the real projectivization of this vector space. So Teichmüller's theorem is that solving this equation, that the mapping from this to Teichmüller space is a homeomorphism. And this, at least, I haven't checked it that carefully, but to my general understanding, this was the second proof, I'm going to say, that Teichmüller space was a cell. The first, in my mind, really is due to Fenchel and Nielsen, which was a little earlier, I believe, than this. But this certainly is the second proof. And this is a more general point of view than Fenchel and Nielsen. All right, now, there's even more to Teichmüller's theorem than this part. There's the fact that, which I'm now going to explain briefly, in this parameterization, the radial rays are geodesics for delta, which is a metric. And I'll describe, it's a simple reason why this is the case. And the simple reason has to do with the composition law is for quasi-conformal maps. Or actually, you don't even have to say quasi-conformal maps. What the chain rule is for this expression. So suppose we have a mapping triangle. Then the Beltrami differential, so this is Beltrami differential. The Beltrami differential for the map up here is given as follows. And so let me explain some of my notation. All right. So I mean that F lambda has Beltrami differential lambda, and correspondingly here, Beltrami differential is always this ratio for the map. So the composition law for a triangle is exactly here. Now, just do a little thought experiment, and that is mu and lambda are tensors. So unless their horizontal and vertical fields match up perfectly, then there's going to be a lot of loss, so to speak, in this combination. When there's going to be cancellation that goes on. And then that shows you that unless the horizontal and vertical fields match up perfectly, that we don't expect the composition, we don't expect this element up here to be a geodesic. All right, we don't expect it to be extremal. At the same time, so let me turn that observation around the other way. Let's be more naive and just look at this part. This is the rule for the formula for holomorphic automorphisms of the unit disk. So think in a very simple-minded way. So what happens if it's the case that mu is a multiple of phi bar over phi, and if lambda is some other multiple, say, of phi bar over phi, then this expression only acts on the s and the k. That is, you can factor out the phi bar over phi, and you can see literally there's no cancellation in the expression. So, and this is actually not just a casual observation. This is, in fact, what I'm telling you is how this works out. And that is, if you have maps which have the same phi bar over phi, and then you take their composition, then this will be a triangle of extremal maps. All three will be extremal. So what that tells us something actually rather fantastic. That tells us that if we consider all the maps which have this Beltrami differential, where zeta is in the unit disk, that tells us that this is parameterizing a whole complex disk worth that's geodesic, totally geodesic. So the statement is then, in this case, the mapping of this into Teichmuller space from the disk, so this is the domain of the map, this mapping, so I should write it here, is an isometry between, well, you know what metric goes with these automorphisms, the hyperbolic metric. So that tells us this mapping is an isometry between disk with hyperbolic metric and Teichmuller metric over here. All right, these disks are very important. So these are two-dimensional, totally geodesic disks. And going back here, the Teichmuller metric is not even C2. So the existence of totally geodesic disks is a very surprising fact. All right. Now these come up a lot, these mappings, and these are called Teichmuller disks. In fact, a little further on in the talk, these are going to get promoted to something even more impressive. All right. Now, this holomorphic quadratic differential and this mapping, or actually just the holomorphic quadratic differential, this gives us, because I've already been referred to it, this gives us a structure on the surface. Well, Now it's a singular flat structure because indeed the holomorphic quadratic differential has zeros. So these formulas don't work at the zeros. All right. Well, what's the flat structure? It's straightforward. When you take antiderivatives, antiderivatives differ by a constant, and also because we took a square root, antiderivatives could differ by a sign. So the flat structure is the charts given by that rule have here's the general overlap. The general overlap formula is just going to be this. All right. Now, particularly about a decade ago, or a little more than a decade ago, it was realized that for what I'm going to be speaking about, there's a much richer structure if we just restrict to the plus. And so this is started a decade ago. Restricting to the plus means coming back here, we need to have well-defined square root. So for the rest of what I'm going to describe people's work, I'm going to, or almost all of it, I guess there are parts that might not need it, but almost all of the rest of what I'm going to describe, I'm going to be assuming that the quadratic differential is the square of an abelian differential. And this is certainly at the beginning. So assume C is omega squared. All right. Now, certainly this gives us a flat structure, sorry, described here. This flat structure, it has singular points. So at the singular points, the total angle around a singular point is always a multiple of 2 pi. And the points that are singular are points where the multiple's greater than 1. So the singularities of the structure will have they'll be of the form of multiples, of integer multiples of 2 pi. And let's say there are S of these. Gauss-Bonnet applies here. It's as if there's Dirac deltas of curvature sitting at the singular points, sitting at the zeros. And the Gauss-Bonnet formula here is certainly then just going to count these integers, and it's in fact the easiest possible thing it could be. So Gauss-Bonnet is just the following. It's the sum of the k's is 2g minus 2. And that matches what we expect because these are zeros now of an abelian differential, and we have to pick up the degree of the abelian differential. All right. Now, how are these structures parameterized? Or how can we parameterize them? So the way that's become clear is the right way because of the results it leads to is by what are called edge vectors. So let me do a picture of what part of one of these structures might look like. So this is the development of the structure, meaning we have this Riemann surface that has this structure. I started unfolding or unrolling the structure onto the plane, and I'm showing you part of that image on the plane. All right. And so let's say in my picture that I have zeros, that is singularities, at these 4 vertices. All right. Then a way to parameterize this structure is by the vectors going between the singularities. And these vectors are well defined because we have a flat structure. And that is the only, especially now, because I restricted to plus, the only change of coordinate is translation. So when I change chart, I'm changed chart only by a translation. So these are called translation structures once we have this condition. And in a translation structure, the vector between 2 points is well defined along the linear direction. All right. So these are called edge vectors, or some people call them edge vectors. And these are, we expect that they're going to be moduli for these structures, or we hope they are. All right, so with this, let me try to make this a little more systematic. So what one does then is the following. One fixes a partition of 2g minus 2. So this could be the sequence of k's. So I'll just write k vector for that. So that's my partition. And then there's introduce the space hk, and this is the space of all translation structures, translation surface structures with this vector of singularities. All right, well, from this description, so let me, back up for a second. All right, so this is the space I want. Now, for the moment, let me consider that we have homotopy marked translation structures, because this is some type of moduli space. And I'll say, make it clear which one it is or what it is. But for the moment, let's say we have a homotopy marking on our translation structures. So that is, we can have them correspond to development or representations. And then once we have a homotopy marking, so with a homotopy marking, so I'll write that this way, I guess. So this would be homotopy marked structures. This, it's not surprising, this is a PL manifold with these coordinates. It's a piecewise linear manifold. All right. So then what happens here, because, well, it'll become clear in a few minutes, but once we remove the homotopy marking, we'll see that this is the quotient, this is an orbifold quotient of this. So in fact, this space is a PL orbifold with these type coordinates. All right. Now, clearly there's another description of what we're talking about, and that's one that's more classical. And what's the other description? The other description is these are geometric pictures, but what we're talking about are abelian differentials. So this is some space of abelian differentials. And what space, so what would be the picture that way? So the picture that way is the following. We have HK, and this sits inside of a abelian, that is, it sits inside of the Hodge bundle of genus G. And this is fibered certainly over the moduli space of curves of genus G. Now, this picture facilitates what I want to describe next, and that is, there's a flow on this space, and the flow is a lift of the geodesic flow of the Teichmuir metric. And so in this context, that's fully appropriate, because this is a bundle over here. So, and in fact, This is not literally true, but I can't resist saying. So you could think this is like the square root of the tangent bundle in some sense, and actually square root of cotangent in some naive sense. And so it's reasonable that we could have the geodesic flow or lift of the geodesic flow acting on this. All right. And then one or two comments before I get into the comments about the flow. In general, these are not connected, but it turns out, so it's very beautiful work of Kontsevich and Zurich. This will have at most 3 components, and the components of this have been classified. So it's known what the pattern is of when it has what number of components. It's also a still open conjecture of Kontsevich that these are always k pi 1s. This is not known to be true, but this gives you an idea of what people think it looks like in the large. All right. Now, when we think of translation structures, we're thinking of a surface presented to us in a very concrete way. And that's good and bad. It's good because we have a very concrete understanding of the surface. It's problematic because whenever you have something presented in a concrete way, that means you've done something equivalent to very much fix a gauge, fix a reference in every possible way. And just to make that clear to you, I'll give an example which you'll be able to figure out yourself what's going on. And that is, in the plane, if I took the torus, which has these generators, this is the square torus. All right. Well, we have the same phenomena going on here, and that is because these surfaces are presented to us in a very concrete way. Well, the surface may have been, in the way we're looking at it, may have been very much drawn out in one direction, and that may not be representative of the geometry of the surface. That may just be the perspective we're looking at the surface from. All right, and what's this about? This is about that, if you like, this is a bundle over the moduli space of curves, and in here we don't have a preferred way to look at a given curve. So you have to be very aware of that. All right, now what's been studied very heavily for the last decade is the dynamics of the flow on this space of structures. All right, and I'll say what the flow is. So back with the composition formula I had with the mu's and the lambdas, explained that these compositions follow the rule for holomorphic automorphisms of the disk. Well, that group's U11, which is just another form of SL2R. So back in that picture where I talked about these Teichmuller disks, SL2R naturally acts on each of these disks, canonically, because of the composition rule. All right, well, what's been studied is the lift of that flow to this case in this setting. In this setting, the description could not be simpler, and it's the following. GL2R acts on HK just by the linear action on edge vectors. All right. So what we have now, which is at this point just a little interesting or intriguing, is we have a GL2R action on this bundle over mg. So still at this point, it would be a question whether or not that's an interesting flow. So let me I'm going to show 3 theorems, which I think make that clear. So the first theorem is not about this flow. The first theorem is about something simpler. The first theorem is about the dynamics on an individual translation surface. So we're not varying the surface. We just have one surface. And we ask, well, could there be interesting dynamics there? And the answer is yes. There's a very beautiful theorem of Kirchhoff, Mazur, and Smiley. And the theorem is the following. For every translation surface, and almost every slope, every infinite line of that slope is equidistributed on the surface. So this is actually, I'm going to say a little surprising because these surfaces, so yes, they have higher genus, so we like to think of them having an Nossoff geodesic flow, but we've done the extreme thing and put a structure on the surface which is a flat structure. And so it's not clear we're going to get how much dynamics we're going to get out of this singular flat structure on the surface. Well, this says that, in fact, we get very nice dynamics. And to remind you, equidistributed means the following. If you take a very long line, finite length, then for any set on the surface, the amount of length in that set divided by the total length will be approximately the ratio of the area of the set over the ratio of the surface. It spends a proportional amount of time in any very long segment spends a proportional amount of time in a set, open set or measurable set. All right. Now, more interesting, so this is entree. Let me go on to another theorem. Yeah.
This is an ergodicity tape result?
Yes, yes. Which is, again, very nice because we're in a flat geometry, so it's not clear if we should have expected that. Singular flat geometry. So the next theorem I'm going to describe is due to Mazur and Veitch. So that's joint work. Here, this is due to each of these independently. They have 2 quite different proofs. So now we're going to talk about GL2R. So the GL2R orbit of almost every translation surface is dense in a connected component of HK. So this is, if you like, towards asking a question of how much ergodicity or how much mixing do we have going on for this GL2R action. All right. And this is certainly very, very nice result. I'm giving the almost every and then There's just an absolute statement as the conclusion. All right. So now let me say one more thing, because this is going to come up in the next result. So back here I described, or gave you a definition of a Teichmuller disk. Then there's the case of a Teichmuller curve. Because and that's related to this question, we start to wonder, what do these orbits look like? All right. So what's a Teichmuller curve? The Teichmuller curve is the following. We take this, and if the image is a subvariety, that is, if the image is a holomorphic curve in M, then it's called a Teichmuller curve. So this means image in M is a subvariety. Right, these are very special and very rare, or rather rare. All right. Now, there are many other results, very, very nice results. Well, in this whole area, then, the meta question had been, what's the general statement about what a GL2 orbit, GL2R orbit looks like? And this is where Eskin, Mirzakhani, and Mohammadi have just this beautiful theorem, which certainly it completely answers the general question, but it now has opened the door to very specialized questions because there's so much more information available now. So let me write down what this theorem is. And again, this is the theorem, at least to my mind, that's responsible for the major reason for Mariam being awarded the Fields Medal. The theorem's the following. The GL2R orbit closure of a translation surface is always an orbifold. And in fact, even more, if we think, so now we're going to talk about in the local manifold cover, because I want to make a statement about what the coordinates look like, describing the orbifold. So in local manifold cover, it's given locally by linear homogeneous equations with R coefficients in the edge vectors. This last part's as nice as could have been expected, certainly. That is, the equations did not, well, they did not a priori need to be linear. They did not need to be homogeneous, and certainly is, well, naively at least, which is really at my level, they could have had complex coefficients because these are complex vectors. But the fact is the equations all have real coefficients. All right, this theorem, so now I want to make quite a few remarks about this. This tells us quite a lot, or has enabled quite a lot. One is, it's an easy fact that there are only countably many such orbifolds. But there's continuums worth of translation surfaces. So these, in some sense, these are special subvarieties, first I say in a general sense, of the moduli space. And they're like, at least I was thinking, there's, in a simplistic terms, they're like some generalization of geodesics. So in manifold, we're used to only having countable number of geodesics. So these are this countable number of submanifolds where the orbit closures, well, orbit closure has to be one of these. Now, since then, or I guess close by time, Simeon Philippe proved that these are always quasi-projective varieties. So they're the richest possible answer you could have expected. Where did the motivation for this come from? The motivation, so for dynamicists, it's well known. This is the counterpart of Ratner's theorem. This is a celebrated theorem of Ratner, which says if you have a G mod gamma, and then if you have an H acting on it, and the H is generated by one parameter unipotent groups, then that the orbit closures for the H action are always sub-homogeneous spaces. So a statement that orbit closures are extremely nice, so the nicest possible thing you might have hoped for, and that they're very rigid. So this is, now Teichner space, and certainly with any geometry, it's not a symmetric space. At the same time, there's a history of many theorems which says that it wants to be like a symmetric space, even though it's definitely not, and it knows it's not one, but it's trying hard. All right. So this is, I'm going to say, a milestone theorem in that direction. And just to give an idea, so there are papers now people are working on coming out with detailed descriptions of what these orbit closures look like. And those papers are all based on starting from this point. And that is that you know ahead of time, or at the very beginning, that an orbit closure is going to be defined by linear homogeneous equations with real coefficients. This gives a lot of structure. All right. Now I have to ask, when did I start?
You have about 15 minutes.
All right. So now, all right, so then, fine. I have to figure out what to do now. All right, so part of this, in all this work, people are thinking of structures in a very geometric way. And when I say that, I now mean geometric in Thurston's sense. So geometry is a word that has many meanings to many people. In fact, an incredible range of meanings. But everyone's reasonably familiar with that. When Thurston said geometric, this was in a synthetic geometric, very literal way. All right. So these surfaces are handled, they're thought of in this very geometric way. And so people, to understand them, need to do deformations of the surfaces. To do this, you don't want to use some general theory like Kodaira-Spencer, because it's not going to preserve the geometric picture. In particular, it's not going to preserve the flat structure or show you how to deform it very well. And so this is where at least the last part of my talk I want to talk about, and that is, so I've been interested in some of the geometric deformations that have come along with these problems, or these handling these questions. So I'm going to give an example of a deformation. So, and this is for starting at the 0 of a quadratic differential. Suppose I have a 0 of a quadratic differential. Then along these lines, the quadratic differential will be negative. Or sorry, the Abelian differential. I want to stick with Abelian. Then here's
Is that z squared or
z squared. Here is a deformation. So deformation is the following. I'm, in a very, if you like, old-fashioned sense, I'm going to cut open. So even though these rays go out, I only want a finite part of the ray, a finite segment on the ray. All right. I'm going to imagine that I have something like a razor and cut the plane open on these segments. And then I want to open it up. And, all right, so. So this is in some, if you partially psychological picture. So imagine I've slid it, the plane in these places. Now since I've slid it, I have at least formally a hexagon. I have 6 sides. All right. Well, I'm going to open it up more just to facilitate picture. So here's my hexagon. And I'm interested in the complement of this region, because remember, I've opened it up. And so the coloring here goes as follows. Then, to do a deformation, what you can do is the following. I want to close this back up again, but before I close it back up, I'm going to rotate by 2 pi over 6. And what is this going to do? And that is, originally this side was paired with this side. And similarly, if I rotate it, but then apply just the inverse map of the map I just applied, what's going to happen is now this side's going to be associated with this side with this side, and this side with this side. All right. And so then you put it back together, and you get this picture. Because, in fact, where the legs are is, remember, over here I'm identifying this side with this side, so the leg is here now. And I identified this side with this side. There's a leg here and a leg here. All right. This is a deformation that people use. And at least when you first see it, this amazing thing is the following. If I start, I'm in the plane. All right. If I start with this Abelian differential, then when I glue this back together, this will be holomorphic on the image. And how do we know that? So I'll tell you how we know that. You all know that. And that is, when I do this identification, I'm identifying isometrically in terms of this measurement along the edges. And so when I identify this side with this, I'm identifying holomorphic functions by a map where the two coincide. This is Schwartz reflection. So this tells you immediately, and I'll even say a little more, this tells you immediately that when I glue this back together, this is at least holomorphic except at the vertices. But then you think isolated singularities. First is one. Now there are 2 ways to see that there's no problem at the vertices. The 2 different ways are you can just compute what's happening to the total angle. And you see that it goes over to what you expect. The other, for people who are particularly non-believers, is the following. And that is the form of the local map from here over to here is, if this is V and this is U, then the form of that map is V cubed equals U. which then certainly means 3v squared dv equals du, which means that du in the domain goes over to a double zero in the range. And similarly, the form of the local map from here over to here is u cubed equals v. And now I'm going to do this same sophisticated calculation. This tells us that u squared du in the domain goes over to non-zero differential in the range. No singularity. So indeed, z squared dz, you do this slicing with razor, put it back together, it goes over a holomorphic quadratic differential. All right, now, being both a geometer and an analyst, I was very intrigued of, well, how are you going to compute what this deformation is? Because we're all want some type of theory where we can make computations. And there, it turns out there's the beautiful theory of conformal maps, which we often don't think about so much. And it's the following. The conformal map from the exterior of this to the exterior of this is well known. In fact, if this has n legs on it, the conformal map is this. This is one of these achievements of conformal mapping theory. This is exactly the map. And so then what is the deformation if you want to make this into a family? The deformation is that first of all, you would scale this construction. So you'd put in a scaling parameter because you want to vary from the identity. So you would do it at scale epsilon, and then just you want to take the derivatives in epsilon. And so I won't write it down, but you can, well, I'll write down one thing and then say you can do the rest. And that is, for this map, then here's an actual realization of this picture. So you introduce the scaled version of this map. And then the mapping I described, the total mapping there is the following. And this is this is n epsilon's the scaling, and this is the inverse map of that. And you can compute the first and second epsilon derivative of this, and you'll get the first and second check co-cycles for the deformation. All right, fine. Now, I guess, all right, so now I have to abbreviate more. So my own project started with Alex Wright asking me for these maps how you might compute the variation of the Riemann period matrix. And when he said this, he meant very much these maps that are geometrically given. And by formula, he meant formula that was useful, let's say, in the Thurston sense. So, well, so here, there's a beautiful approach due to Schiffer. And the Schiffer, so he's actually, there's a deformation that goes by his name that he's very well known for. And the deformation is the following. If you have a chart, and you have a curve that bounds a disk in the chart, and then you have a holomorphic function defined in the neighborhood of the curve. So I'm going to say that's R of z. his deformation's the following. His deformation is that you take the exterior of the curve, take that region, and then you take the image of the curve under this mapping. So this is, you consider mapping z plus r of z. And you get image of curve. His deformation is that you're going to glue the exterior of gamma to the interior of the image. And the gluing is exactly this. All right, so first of all, this is very geometric. Now, if you think a little more about it, you realize this is precisely check cohomology description of a deformation. Because check cohomology has to do with overlap. Well, here, initially, he's not giving us an overlap because the cocycle, so to speak, lives just on the curve. But he's working with holomorphic functions. So holomorphic functions, it doesn't matter whether we work on a curve or a neighborhood of the curve, it's the same relation. And so this is exactly the check description. All right, now I have to ask, how much time am I? All right. So then I can explain the two formulas that are on the board, and that's going to be about it. All right. So for Schiffer, he has a very, and I'm referring to his book, Schiffer and Spencer. He has a very definite point of view of how to understand Riemann surfaces and how to understand their deformations. And it's not an unusual view, but he carries it very far. So for him, understanding Riemann surface and deformations is only about the Green's function. The Green's function is everything. All right, now he wants everything to be explicit. So he gets the Green's, he does the following for the Green's function. So he starts with the abelian differential of the third kind. So this is abelian differential, which has poles at Q0 and Q1. And it has, just to explain his notation, it has residue -1 at Q0 and residue +1 at Q1. And then, because he's classically trained, the next thing he takes, or what's obvious for him, is the abelian integral, the antiderivative of this. Oh, sorry, one more statement. It's of the third kind. So the third kind means all the periods have vanishing real part. So then he takes the antiderivative of this, which at first, because we have modern training, we kind of screech and we go, but that's a multi-valued function. All right, but he's interested in the real part because that's when he's thinking of Green's function. Well, I'm going to write a little more. The real part is not multi-valued because of this condition. And the real part, because it's antiderivative, it has a logarithmic pole here and a logarithmic pole here. And to make his formulas come out very nice, pretty, which he likes, or very symmetric, he actually symmetrizes this expression, and he looks at the following. This is a function of 4 variables. So I refer to it or think of it as it's the double pole Green's function. So there's a source and a sink. So there's no problem about compact Riemann surfaces don't have a Green's function. All right, compact Riemann surfaces can have a Green's function. You just have to have that the net charge is 0. All right. Well, he symmetrizes it this way because then, on purpose, this function is symmetric if you interchange, and if you flip one of these pairs, it just goes to its negative. So this function has a lot of symmetry in it. All right. For Schiffer, this is the central quantity to study. And so, first of all, let me show you theorem here. So this is my extension of his theorem, and that is this is a second order expansion for the variation of the Green's function. So this is the same V that's over there. And you recognize all these quantities. And here, because I'm doing second order deformation theory, here's the cocycle. And then you see how it enters. All right. And now what's lambda? So lambda is something I call it's going to be just a variant of V, and it's something I call the Abelian kernel. And let me give you the definition of that, and then just say what the corollary shows over there. Here. So lambda is the following. It's going to be the second derivative of V, or if you like, first derivative of d omega. So lambda is minus 2 over pi partial V with respect to P and Q. So what's sitting here, this is really just notational. This is just some derivative of omega again. All right. Now, what's great, and certainly he had this in mind, what's great about this setup is, what are we looking at? We're looking, all right, now, elementary check theory is we want R1 and R2. So R1 and R2, they had to be holomorphic in neighborhood of curve. Well, basic check theory, you know, if they're holomorphic across the disk, then they're the trivial deformation. So to be interesting deformation, R1 and R2 they should either be not extendable across the disk, but that's rather exotic, or more practically, R1 and R2 should have poles in the interior. All right. So in practice, particularly for Schiffer, he had in mind just that R1 and R2 have poles in the interior, and so then we're just computing residues because we have functions, we have curved functions, meromorphic inside, holomorphic. And the setup of this, all the points P, Q, P naught, Q naught are outside of gamma. All right. Then finally, so I'll stop with this. Finally, I apply this to get second order deformation of the Riemann period matrix. So here's expansion, second order expansion for Riemann period matrix. And this actually addresses the question Alex originally asked me. And so what's the notation here? The notation here is omega u's are a basis for the Abelian differentials. Then I'm in a local coordinate. So when I write omega u, I mean the coefficient of the tensor in that local coordinate. So that's what this means. And then down here, we have derivative. This means derivative of the coefficient in that local coordinate. And similarly, that's what here is here. The only last thing that's not explained is what's this little lambda? This little lambda is a regularization on the diagonal. This has a double order pole singularity on the diagonal. And the in that formula, what enters from here, because it's sitting here, is you need the regularized value of this on the diagonal. That is, you subtract off the known double pole and then take the limit to get the regularized value. All right, and so that's what this is. And this formula already shows us lots of things. So it shows us, just as a general statement, the variation of the entries of the Riemann period matrix only depend on derivatives of the differentials corresponding which entry in the period matrix you're sitting at. And you can see even what order you need to know the differential to. And in particular, so one thing took me a lot of time and effort is I have a whole collection of examples of deformations. They all give 0 for this because remember back here, differential glued up to differential after the surgery, so there was no changing of the periods involved. And so it should be the case, that example and other examples, they all annihilate this expression that's sitting on the right. And I'll stop here.